Hi, CLB students. So you have your reactors or your anaerobic digesters, your bag now. And apart from being able to operate it, we're going to be spending a lot of time on that. We got to go a bit further and constantly think of the process that's happening within your reactor. So what's in the bag? Well, basically bacteria and archaea. It's quite interesting because the bacteria does the initial breakdown while the archaea or the methanogens takes the acetate, the CO2 and the hydrogen and makes methane, which is the gas that we're going to be burning to cook fuel in the townships. So it's very interesting. These two different domains are in a delicate balance. You're going to measure pH and you will find that bacteria tends to lower the pH while the archaea brings the pH up. You need a stable pH, which you will be measuring, and that interplay between these two colonies is very important. You need harmony in there for the system to operate healthily. So what's in the bag? You might think it's just bacteria and archaea. I see it differently. I see a teacher in the bag. Okay, think of those microbial consortia or microbial organisms combined together as the teacher of nature. And hopefully throughout the semester, that teacher will teach you a few things. Okay, guys, it's not really about marks. It's about how much you can understand about how life works and how you can apply chemical engineering to improve that understanding. So let's get on. Guys, before we get into some technical aspects, just remember why we're doing this project. The bigger vision, and it's important because you guys are contributing towards this vision, and it's all about sustainable living in African informal settlements. So we'll be developing. We've decided in this project we're going for really cheap containers for the digesters. So we're not going with rigid plastic. We're going with plastic bags, which is very affordable yet doable. So that decision has been made, but now a lot of development work needs to be performed, and the work that you are doing is contributing to our understanding and our development towards implementing this project. So always keep this in mind. Your bag might be 10 liters, but at the back of your head, you're thinking an 800-liter bag somewhere in a trench outside where a similar process is occurring. Okay, so now that each group has a baby, we had to scramble to get 7 babies out. They might not be all perfectly healthy, and for now it's all about just getting the digester to perform consistently over the feed cycles that we're supplying. So you might ask, when do I know my baby is healthy? Well, first of all, you need repeatable data in terms of the amount of gas you make. For the feed, we've been doing some experiments prior to you guys. You need to get about 11 to 14 liters of biogas in 48 hours. So over the weekend, when there's free days, you can see if you reach a total combined biogas of in the vicinity of 11 to 14 liters. If you get that consistently and your pH is stable in your digestate, then you will be ready to implement your experimental plan. It'll probably take a week or two for some of those reactors, but I want you to start thinking, once I've signed off on your vessel being stable, what's the next step? What are we going to change? What are we going to investigate? The system is slow, so we got to plan carefully beforehand. So you can start thinking about options in terms of what you want to do. But this is more or less what a healthy baby, these figures are more or less what a healthy baby looks like. Okay, so to understand that smoothie that we make from the vegetables, we got to think about it in terms of how much substrate is there that can be converted to biogas. Okay, and we have a look at substrate. Most of you did CBI, so you have some background. Please note, and I've got over here, let me just get my color pen. So in that smoothie, it's really water that encapsulates solids. And the solids itself, some of them are digestible and some are non-digestible. These little black dots are just the lignin parts, or the parts that cannot be digested by the organisms. So the first question is, because we're going to be working on 48-hour cycles twice a week, and then a 72-hour cycle after that, the question is, you're going to find you make a lot of biogas. So our calculations, and this is not a figure, this is a figure that might change, but in terms of the amount of biogas you make per gram total solids, our estimate, very important estimate at this stage, is slightly higher than 400 milliliters per gram of solid. So it's important you make gas, but after 48 hours, you might still have substrate that's not converted. In our CBI modeling, it was very slow. This process seems to be a bit faster than the models we employed in CBI. But the question is, and let's call this the latent fraction, after 48 hours, how much of that smoothie that you've added is unconverted, but it can still make biogas at a later stage? That will be after 48 hours. We want to quantify that. We're not exactly sure as to what that number is, and hopefully your experiments will help us to elucidate that. So also remember the recalcitrant, that's the indigestible fraction. Our estimates at this stage is saying that about 40% on a mass basis of the solid won't be converted. That means there's a solid buildup in the reactor. But that's also beneficial because we realize that most of the bacteria and archaea are not suspended in the liquid, but they're rather sitting on the solids, whether it's a recalcitrant or whether it's substrate. It's biofilms. Biofilms is immobilized. They attach to surfaces, populations that performs most of the work. We've realized this because if we just take the clear liquid out and we add smoothie to that, we find that the digestion rate is horribly slow. But as soon as we mix some of the solids into the mixture and use that as a culture, we get consistent and fast behavior of the digestion. So these numbers that I give you, they're not fixed yet, but we're constantly working on obtaining better estimates and for these numbers. So in the previous slide, the question was, in 48 hours, how much of the solids have converted to CO2 and methane biogas? We can, of course, now ask the question, if I leave infinite time and convert everything that's convertible, how much biogas can I make from the solids that I feed? Okay, there's two ways to approach this. You can go theoretically. You can just see a simple mass balance like we've done in CBI over here. By the way, the elemental composition of your slurry, at a stage we'll do an analysis and we'll be able to give you maybe a bit more accurate numbers than the one supplied here. But here it's a very simple calculation, not including the bacterial growth as part of the mole balance. You can do a simple calculation, and mine suggests that if 40%, this is now on a C mole basis, so it's not exactly mass basis, but roughly 40%, if 40% is unconverted, you should be able theoretically to make 740 milliliters per gram of total solid. There is some questions because we talked about 450 that we make in 48 hours. There might be an issue with CO2 dissolving into your gas capturer, so that you've actually made CO2 that you don't measure in the volume, because the CO2 will dissolve in the liquid and then actually diffuse out into the air. So that's something that also needs to be quantified to see how much biogas can be made and how much we are making. One thing that I want you to read about is called the biochemical methane potential, BMP. Those are tests where you work in a batch system, you put in your slurry, and you see over a long period of time how much gas you make. By the way, I see I'm in front of this picture, but Kyla is doing an MSc on your exact system. She's got a bit more control in terms of pH, in terms of mixing, in terms of a few other things, smaller systems, but she's working with exactly your slurry. So I encourage you to contact her, start talking with her, especially when it comes to the biomethane potential. She will tell you, we're struggling because the problem with getting a good BMP value is that you need sufficient amount of bacteria and archaea. You only get that from the solids themselves. I've talked about the biofilms being on the solids. And as soon as you move solids into a reactor where you put slurry in as well, you're not exactly sure how much substrate is still in that solid where the biofilms are growing on. So I actually encourage you to speak to Kyla, and maybe we can actually set you up with a very small digester and a gas capturing device. Go visit her in the lab. She can show you where you can maybe contribute to giving us an experimental estimate of how much biogas can be made from our specific slurry. So start thinking about that. So then, the plan is that each of these 7 fermenters will test something specific. First of all, you need to get your baby healthy and your biogas production stable. Only after that, when I've signed off on your stability, you can start, varying the parameters of your run. It's important not to vary too many of them together. So you need to come up with a plan in terms of how you want to execute your experiment. So very important, we're not writing academic papers, okay? We're not trying to find something cool and report it. We're rather asking ourselves the whole time, this investigation that I'm suggesting, how will it assist in the development of the township bag digester? So you think about things like temperature variation. It's going to be different with that black bag in the trench. Next year, we're going to perform a lot of experiments, probably CSC projects, where we have a look at how we can manage temperature within the bag by really harvesting sunlight. We'll use black bags. We'll use the radiation need into the soil to see what temperatures can be obtained and what the stability of those temperatures will be, because it will typically go through day and night cycles. So, simple things to think about. We can consider changing feedstock, because obviously we've made up a mixture which we just say presents organic waste from the townships. That's an idea. Maybe you want to play a little bit around with temperature. By the way, I've told you, you can record your temperature with your device and get a better idea as to how stable your temperature is in that bag in the lab. Maybe we want to play with temperature. We spoke about the latent fraction. Maybe you can design an experiment where you look at obtaining the amount that's not converted in 48 hours, because it does appear that more than 50%, even more than 50% is converted within the first 48 hours. You can do different feed cycles, whatever you're thinking about. We can't test too many things, because we got to show a clear deviation from our normal state, which a lot of you are still just achieving, and that's to get your 11 to 14 liters of biogas per 48 hours. So just start thinking, because soon we'll start have meetings where you as a group will start discussing with me your plans for your anaerobic digester. So lastly, guys, we've now got our reactors, we've got our schedule. We'll be setting up numerous meetings. We've got a fancy venue, 451 in Engineering 2, where I'll be meeting with each of your group. It will be an hour meeting every second week or fortnight. So those schedules will come up. We'll start next week, probably Wednesday next week. For those doing the kinetics, all of you doing the kinetics experiments, we'll have separate feedback sessions for the interpretation of your results, and we'll mix it up a little bit by maybe taking group 1A combined with group 2B, vice versa, so that, your group as a whole, might help one another with your experiment, but in your feedback session, you will be mixed with another group. In that feedback session, I'll give you more detail on what's required. But the manual is out. I've posted, the notebooks of those experiments. I think the first kinetic experiment is starting next Wednesday. Okay, So that's it, guys. Take care of your babies and get it to a healthy, stable state, and start thinking what you're going to do when your baby is at a healthy, stable state. Cheerio. We'll talk again.